It's great to be here. Appreciate the opportunity. Thank you very much. As we're getting started here, just working our way through the small talk, I'm going to hopefully get some assistance to distribute a few props around the room. There's not enough for everyone to get one, but hopefully people can kind of share them in particular, zones of the room. There's only 8 of them, so you'll have to share. Please do be careful. These are the most expensive wine glasses that you can purchase at Dollar Tree. They're also the cheapest that you can purchase at Dollar Tree. So it's funny how that works. And some of you may already know the punchline to this setup here. Wait for those to get distributed around there. And just hang on to those and we'll have a chance to look through them. Okay, so I'm going to talk to you about looking through gravitational lenses. So you already kind of know what these things are here. These are Einstein Ring gravitational lenses. But, has anybody seen pictures of these sorts of things before? Does anyone know what they are, aside from just what the words say they are? No. Anyone want to volunteer and explain it?
Distant galaxies, which are behind foreground galaxies, and when the light gets bent around like this.
Excellent, yes, that's exactly right. So these are, each one of these little panels here is, actually has 2, well, in some cases even more than 2, but basically 2 galaxies in it. There's this orangish one and then there's this bluish one. And they're along the same line of sight out into the universe. But the orangish reddish one is much closer. This is, a few billion light years away, and these funny ring-shaped ones are a few more billion light years away. Give or take. And they look like this because the gravity of this more nearby galaxy is actually bending the light, the more distant one, into this crazy sort of configuration here. And we call these things Einstein Rings for reasons that we will that may already be apparent, but we'll explain a little bit more as we go. So I appreciate Robert's introduction to models and data, and I actually have a little bit more nuanced, kind of like in-between pace between models and data. So what do you think? All these on the right-hand side here, what do you think these are?
Some separation of that.
So these are all models over here. So this is actual data here. This is just a different colored version of one of these same sort of images here. This is taken with the Hubble Space Telescope. This is data here, but actually the colors in this data are informed by the model. So this is like a model-enhanced data image. So it's a little bit dishonest in some ways, but full disclosure, you heard it from me. And incidentally, the size of this thing, you could fit probably about, if you imagine the size of the full moon on the sky, you could fit about 1,000 of these across the full moon. So that's the kind of the size we're talking about. It's a pretty small little point on the sky, and that's why we need in this case, we need Hubble Space Telescope imaging, or we need some sort of way of seeing these things in really high resolution to be able to discern these details here. So what you see here, this is a model, or a sort of if you can think of this as sort of pulling this image apart into the parts that make it up. This is the model for this foreground, what we call the foreground galaxy here. This is the model for this weird-shaped galaxy around the outside here. And then this is actually a model for what this thing would look like if that thing weren't there. It would look more boring. It would just be kind of just a blue blob instead of a blue kind of pair of horseshoes or whatever you want to call it. So these are gravitational lenses. They're galaxies warping the images of other galaxies. So that's pretty neat. And what I'm going to talk to you here about, and hopefully give you a decent understanding of, is first of all, well, how does this work? How does this happen? What's the history of this phenomenon in terms of our understanding of it and our observation of it throughout the universe? And then finally, what is it actually good for? So these things look really neat, but people say, okay, well then maybe you're just one of the insults that often gets leveled at astronomers that we're just collecting butterflies. Okay, that's great, but that's just butterfly collecting, which I think is a vicious slander against butterfly collectors. But anyway, but just in case anybody's worried, there are actually many different quantitative scientific applications of these. So we can turn pretty pictures into boring figures with the best of them. So, okay, but what's really happening here? A good way to get a feel for this, and now this is to introduce the purpose of these props that we have. What's happening is really an optical effect, a lensing effect, quite literally. Only instead of glass or water or plastic or whatever you might imagine making lenses out of, it's actually the curvature, the gravity, and the curvature of space-time itself that are creating a lensing effect. But qualitatively, it's very similar to the sort of effect that you would see just by the optical lensing effects of a dot, a sort of red and black dot like that one on the left, by the base of a wine glass, or I believe that's actually a margarita glass, not a wine glass. So you can try holding it up. You want to hold it at kind of an angle, maybe at arm's length, and just kind of move it around and put it along your line of sight. You don't want to look through the actual bowl. You want to be looking through the base of the wine glass. You probably won't be able to get an image that clean because, again, these are cheap wine glasses and they got some kind of bumps and ridges and wiggles in them that sort of mess up the picture. But I think if you sort of play around with how you position it and how you move it back and forth, you can again, just in a qualitative sense, get a feel for how an image like that of just a what we can imagine is a regular looking normal galaxy turns into some weird sort of arc and counter image, multiple images of the same galaxy. So I'll give everyone I'll put this same slide back up at the end as well, and give people who don't have a chance to people who don't have a chance now can try it again toward the end. I'll leave it up for another minute or so here. Actually, this one can kind of circulate as well for anyone who's looking for another one.
You guys on the car? You want to try?
And again, you want to kind of be looking at an angle, so you're not looking through the actual wine holding part of it, but rather looking just through the base.
I can't see through the end of this map without looking inside.
So I'll put this. I'll leave this slide up at the very end for folks who can check this out more at their leisure. But yeah, that's basically it. So end of talk. So okay, no, really, what's going on here? So most of the kinds of, when you think of a lens, actually made of glass or plastic or whatever it might be, magnifying glass or something that's going to form an image, it's going to focus rays. The diagram for something like that looks like this, and basically the most important point of what's going on is to focus light coming in from who knows where down to a point where you're gonna put some film or like a digital detector here. The important thing about this kind of lens is that the further you go out from the center of the lens, the more the rays of light are getting bent. So out here they're getting bent through quite dramatic angles. Here, not so much. Anything that's coming right through the center is actually not going to get bent at all. So for a gravitational lens, and coincidentally for the foot of a wine glass as well, it goes the other way. So the further out you are, the less bending there is, and then the more you go in towards the center, the more dramatically these rays of light get bent. And that's why the performance of the base of a wine glass is a terrible lens. You wouldn't want to put it in your eyeglasses or try to use it to like cook ants on the sidewalk on a hot day or anything. It's not a function for that. But it does produce these kind of weird looking images that, well, they look cool. comparable to pictures of butterflies, or like butterflies pinned on a, like whatever one of those cases is that people with dead butterflies in. Okay, so this is basically why we call it a lens, but it doesn't behave like a lens, and this is why. And it's the same reason why the base of a wine glass doesn't work well as a lens either. Actually, a way to think about this, another way to refer to it is not actually as a lens, but as a mirage. It's sort of like a mirage effect. In fact, I'm told that, maybe somebody can confirm this, I'm told that in French, they are actually not referred to as gravitational lenses. They are referred to as gravitational mirages. Mirage gravitationnel, or however you say it. Which is actually it's a more accurate description of the phenomenon, because it doesn't actually function as a lens in any sense that we commonly understand that term. And again, you can understand it like you understand the mirage on a hot day if you're looking down a road. If you look straight ahead, you see the car in front of you. If you look up, you see the sky. If you look down below the car, you also see the sky, and that's because the rays of light, based on how the density of the air varies, are bending in funny ways. And you're seeing the sky on two different sides of the car, even though you know it's not really like that. So one of the great things about living and working in this particular era of astronomy is that we don't find these things just by onesies and twosies now. Since we have really huge projects surveying huge areas of the sky, we've actually been able to find hundreds, and soon it will be thousands of examples of such things, and we can actually use them for doing statistical experiments in all sorts of different ways, and I'll talk to you as we go forward about a few of those particular applications. This is just a larger montage from a slightly later year of a lot of different gravitational lenses, again seen with the Hubble Space Telescope. These are data, again, enhanced by with the color provided by informed by the models. So now we're going to take a pause for a quiz, and the quiz is motivated by the fact that in talking about these things, it's helpful to establish some sense of scale, what kind of length scales we're talking about, because they're really just ridiculous numbers that we throw around in astronomy, and you never get used to them. It's, there's trillions of this and like billions of trillions of that. You just kind of have to remember them or know where to look them up sometimes, because they don't make sense in any way that like the distance from here to there does. So the quiz isn't quite this. This is setting up the quiz question. So we're going to think about the distances from the Earth to various other interesting points in the universe. The sun is obviously interesting. There's a particular distance from the Earth to the sun. And then there's Alpha Centauri, which is a binary star, which at least last I checked, was the closest star other than the sun to us. Although there's probably another one that, for all I know, somebody's even discovered and made a press release about. But anyway, Alpha Centauri is more famous. So that's the closest star other than the sun. The sun and Alpha Centauri A and B are all stars, along with billions or hundreds of billions others within the Milky Way. And the Milky Way is a spiral galaxy, and it has outskirts and it has a center, and we kind of live in the suburbs. But there is a downtown. That's where our supermassive black hole lives. So the center of the Milky Way galaxy is an important place in our particular corner of the universe. And then if you move beyond that, there are other galaxies out there, of course. And the most nearby kind of significant galaxy that's like, comparable to us, it's like the Minneapolis to our St. Paul, or the Fort Worth to our Dallas, or whatever the right analogy is the Andromeda Galaxy. So that's the closest galaxy other than our own. And then beyond that, you can say, all right, how much farther can you go? Well, let's consider the edge of the visible universe. We actually know the distance to that very precisely now. And we assume there's something beyond that, but we can't actually see past it. So the question is not what are these distances. The question is, as you step up from the sun to Alpha Centauri, the distance from the Earth to the sun versus the distance from the sun from the Earth to Alpha Centauri, that's a certain factor of increase. And then the distance from the Earth to Alpha Centauri versus the distance from Earth to the center of the Milky Way, that's another. So you remember that Powers of 10 movie? So these are all greater than powers of 10, but it's you're getting farther and farther away by sort of big factors. But the question is how big? And sort of going from each of these steps to the next, the question is which is the greatest factor of increase? Where do you multiply the distance greatest in terms of these 4 steps from going to the sun, going to a nearby star, going instead of the Milky Way, going next door, and then going to the edge of the universe?
D.
Right here.
D.
D. Is that right? D.
No.
B.
Okay, we got a D and a B. Do people want to? I don't know if people get to do process of elimination. Maybe that's.
Oh yeah.
I probably wouldn't know the answer to this if I was you. I only know this.
So it's not B.
It's not B either. No.
Here.
Go for C.
So he says A.
8.5 light minutes to 4 light minutes.
Really?
Yeah, so here are the distances, and again, you can see that they're all just ridiculously big numbers. So what are you supposed to do with these? You divide them, obviously, and that's what you get. So it is A. So it's actually kind of funny because, I mean, the universe is a big place, but one of the kind of the qualitatively biggest aspects of our universe is how far it is from our star to the nearest stars in our galaxy. That's actually one of the biggest leaps out there in terms of all possible leaps you can make. So something to keep in mind when people talk about colonizing other stellar systems. Okay, so that was our quiz. So now let's go back to history. So where did our understanding of this phenomenon of gravitational lensing come from? Where did it start? Well, as with a lot of things, really it does start with Einstein. And Einstein had a theory of gravity called general relativity, which describes gravity not in terms of magical action at a distance, but actually describes it in terms of the curvature of space-time. And one of the predictions of Einstein's theory of gravity was that just in the same way that the gravity of something like the sun bends the path of massive objects from straight lines into circles or ellipses or hyperbole or what have you, it would also bend the paths that photons, particles of light, travel on as they pass by. But it predicted that the angle through which photons would bend would be twice as much as the angle through which massive particles traveling at something other than the speed of light would bend. So this is one of the most important early predictions of Einstein's theory of gravity, that light would be bent by the action of gravity, light paths. And this is commonly regarded as the first sort of experimental confirmation of a prediction of Einstein's theory of gravity. There were also, I guess you call them retrodictions, involving the orbit of Mercury that, in a quantitative sense, are I think more compelling than what I'm about to describe. But this was the first sort of prediction and confirmation, and it was done by an expedition, I guess, led by Arthur Eddington in 1919. To look at what happens to the position of stars that happen to be around the sun during a solar eclipse. Did anybody go visit see the total solar eclipse that happened recently? Yeah, so this is an experiment you only do during a total solar eclipse because you can see stars when the sun is out. So say this is where the stars are when the sun's not in between them. And the prediction of Einstein's theory of gravity is that that's going to happen. They're going to be in a different position. And during an eclipse, you can measure that. And then when the sun's gone away, you can just measure them at nighttime, and you can look at the difference and see whether or not things work out. So I said that gravity, so basically what's happening is the gravity of the sun is bending the paths of light, bending the photons coming from the star to your eye as they pass by the sun. Why do they go out like that? You sort of intuitively, you're like, all right, the gravity is kind of pulling things in, so shouldn't the positions be closer in during the eclipse, not farther out? Because they get pushed farther out rather than getting pulled further in. it's easier to understand that if you consider the sort of the side-on perspective of things. So that's what it looks like. You know, you're looking out just straight out at a star. There's no sun there. But when the sun's there are these bent paths of light, and so you see the ray of light that comes off a star like this. You know, without the sun there, it would have just kept going off to who knows where. But since the sun's there, it gets bent, comes into your line of sight. But then you look out there and you say, oh, it looks like it's right here. So that's why the apparent positions get pushed out like that. And so this is kind of the initial sort of foundational basis for gravitational lensing in some sense. But this is, you know, this is a very subtle effect, and it's nothing like those dramatic rings and arcs and crazy, funny-looking images that we saw at the outset. So what about actual what we call now gravitational lensing? How did that idea come about? So the first thing to note is that it was actually considered by two different people before it was considered by Einstein. Somebody named Lodge and somebody named Schwolson. Both wrote about this before Einstein wrote about it in 1936. The fact that we credit Einstein with this is a good illustration of I think in the Bible it says, to them that have shall be given. So those that already get a lot of credit tend to get even more. And that's happened for Einstein here in the case that we really should call these Lodge rings or Schwolson rings, but we don't, unfortunately. So this was a paper that Einstein wrote in 1936. If you can even call it a paper, it's probably like, I don't know, 3 or 4 column inches. You can't write papers like this anymore. Yeah, I used to be able to write papers that were really just like letters to the editor. And so this is really short. It's not even a paper, it's a letter. And if you read it, it basically goes something like, Mr. So-and-so asked me about this thing, so I did some calculations, and this is what I found, and I hope he leaves me alone now because it's not really interesting, and we shouldn't think about it anymore. So I'm paraphrasing the sort of the setup in terms of, but he did describe the phenomenon. He said, he was thinking about stars. He wasn't thinking about galaxies. So he said, if you have one star go behind another, yeah, the gravity of the star in the foreground would make a ring image out of the star in the background when they pass in terrific alignment. So that's what would happen. But he said, of course, and this is an exact quote, of course there is no hope of observing this phenomenon directly. Yeah, that's that. Actually, 1 year later, or 1 year, ish later, Fritz Zwicky published another paper where he said, well, yeah, stars, that's one thing, but if you consider galaxies, or what they used to call extragalactic nebulae, they offer a much better chance than stars for observing this gravitational lens effect. And he actually went on to predict the sort of the rough frequency with which we would observe these things, and he also described some of the ways in which they might actually be useful for making astrophysical measurements. And the most important thing that he pointed out is that you could actually use this as a way of measuring the masses of astrophysical objects, of galaxies in this case. You could use this as a way of in some sense, weighing galaxies. And the way that works is just that if you have, now imagine these are galaxies, not stars, or you can imagine they're whatever they are. They could be stars too. You have some mass here and you have some source of light here. The more mass you have, the bigger of a ring you get. So there's a reasonably straightforward mathematical way, if you know the distances involved, of translating the angular size of the ring that you measure to the mass of the object that's performing this lensing effect. And that's really the core of the utility of this very interesting and beautiful phenomenon for doing quantitative astrophysics. It's a way of measuring masses. And masses are very hard to measure in astronomy generally. But angles, you can measure the angular size of these rings. We're very good at measuring angles. That's in our wheelhouse. So if we can turn a measurement of an angle into a measurement of a mass, we can win big. So this is all just speculative at this point in the 30s. So now you got to fast forward 40 years or so to the 70s, late 70s, to the first actual bona fide discovery of this phenomenon. And that was this what's called a double quasar. This is 2 images of a single quasar, an active galactic nucleus, like Robert was talking about, So that's the bottom and the top spot there, and then the middle spot is the galaxy that's whose gravity is splitting this one image into two. And then over the subsequent years, there were discoveries of other sorts of things. So what was known as the Einstein Cross. This is 4 images of a single quasar. This is a particular early example of a so-called Einstein ring. This is a galaxy that's being lensed by another galaxy. And if you go even further forward, we actually see examples of what are known as clusters of galaxies. These are big collections of galaxies bound together by their mutual gravity and by some common mass of what we call as dark matter here. And so one of the things, for instance, that you can now you can see another potential utility of the gravitational lens effect is this is the image of a single galaxy that's been stretched out into this huge long arc here. We call them a giant arc. So another useful function of gravitational lenses is that they actually provide very magnified images of very distant galaxies. So it's a way of getting an additional boost of magnification to be able to see things that are otherwise would be so far away and so faint that you wouldn't be able to study them. The price you pay is they're very distorted, but you can undo that distortion if you model the effect correctly. And then, of course, we also have lots of examples of lensing by individual galaxies. So again, in each case here, we're able to use the size of this ring as a measurement of the mass of the galaxy that's doing the lensing. And that's interesting just from a general sort of measuring and learning about the universe point of view. But one of the things that's particularly interesting, I mentioned dark matter already. One of the things that's particularly interesting and puzzling and important and essential about galaxies is that the stars that you see are only part of the picture. And all lines of evidence that we have point to the fact that that galaxies exist in the center of larger, more extended, more massive concentrations of some sort of matter that we call dark matter, because we don't know what else to call it, and we don't have any other better idea for what it might be. We can't see it, it doesn't give off light, but it makes its presence felt through gravity. And the gravitational lens effect is particularly useful because it's a way of measuring the combined mass of stars and of dark matter within a galaxy or within a cluster of galaxies. And this is really one of the most important applications of the gravitational lensing effect, is being able to use it to decompose exactly how many stars and how much dark matter is present in any given galaxy or in some population of galaxies that you might want to slice and dice up in some particular way. This is just a sort of semi-schematic figure from a paper showing how the total signal from gravitational lensing plus the signal from just measuring the starlight and translating that into stellar mass can pull apart the contribution from stars and the contribution from dark matter to understand in more detail how galaxies are constructed in all their component parts. So that's on the galaxy scale. Another important application on the clusters of galaxy scale, some of you may be familiar with this. This is actually a picture, this is another one of these. There's some data here, there's some models. The blue here is models for where the mass is, the mass producing gravitational lensing effects. You can't see the actual lensing images. There's some strong and there's some weak features, but overall they don't show up in this image here. The gravitational lensing says that this is where the mass is. X-ray images, X-ray space telescope images show that the hot gas is located where this pink light is here, pinkish or magenta. This is a case where two clusters of galaxies are crashing into each other. There's a shock front here associated with these two gas clumps hitting each other at super fast speeds. But the matter actually just sails right through. This is the dark matter and the galaxies together. You can imagine this cluster started over here, this one started over here. They were attracted to one another through gravity. The gas had this tremendous shock collision, but the mass in the form of dark matter and also the stars in these galaxies just sailed right through almost as if the other cluster wasn't there. And this is one of the strongest pieces of evidence we have that what we think of as dark matter, kind of dark matter, not just some thing about gravity that we haven't quite nailed down. So, to go back now to sort of close the loop, if you recall, Einstein was thinking about gravitational lensing in terms of stars, and remarked that you'd never hope of actually seeing it. So in one sense he was right. We haven't actually seen Einstein rings at the scale of individual stars. But if you imagine looking towards the center of our Milky Way galaxy, there's just a great density of stars across the image, and now you imagine these stars are all at different depths along the line of sight, different distances, and all of these stars here have motion in the plane of the sky. They have motion along the line of sight, and over a large enough image like this, if you wait long enough and if you keep watching long enough, you'll find that one star happens to pass right behind another one. And you don't get to see an Einstein ring, because that ring, I mean, it's there, but it's too small. And we don't have any telescopes that are good enough to resolve that image. But it does happen, and what you can observe, you can't observe a ring, but you can observe that the brightness of the star that's passing behind can get amplified, and sometimes by very, very great factors. And this is what we call the microlensing effect. So we only see it show up again when one star passes in front of another, and we see the effect show up as the more distant star gets brighter, and then it gets fainter, and it gets brighter and fainter by a particular sort of shape or pattern here. If you look at how bright it is versus time, it's a nice symmetric regular curve here, and the shape of that curve is directly related to the mass. It's related to the distances and the masses of the mass of the more nearby star. It's also related to how precisely aligned they are as the one passes by the other. So this effect was used to actually rule out what were known as, I think they were called machos, right? These were dark stars, or something like massive compact halo objects. That was one theory for what dark matter might be. It doesn't explain all of the observational phenomena of dark matter across all scales of the universe, but it conceivably could have made sense within our galaxy. But there really aren't enough of these microlensing events to be explained by a significant population of dark stars, or machos as they're called. So we know that dark matter isn't in the form of stellar mass objects, and that was another important result of gravitational lensing on the scale of stars. We do so. There's another. You'll see that I've strategically blocked out a little piece of the so-called light curve here, and the reason for that is that there's an additional application of gravitational microlensing, which is that you can actually use it to find planets around other stars. Because the gravity of the planet kind of perturbs the gravitational field of the star, and depending on the alignment of the star passing through the background, you can get these other little anomalous magnification events that can be used to infer the mass of planets around other stars. This is a particularly simple example here in terms of what the light curve looks like. I believe this is due to a planet that was dubbed hot because it's like super cold, like Empire Strikes Back. I don't know if anybody actually calls it that or if that was just in the press release. So that's a simple one, but there are more complex ones as well. There are people who make their careers out of translating these complex microlensing phenomenology light curves into measurements about the planets orbiting other stars. This one in particular is a system of a star that has basically an analog of Jupiter and Saturn. So you're seeing the effects of two different planets around a single star. And so the gravitational field is more complicated, and the magnification pattern is also more complicated. And then on the largest scales, if you now consider again, this is a picture of the edge of the observable universe taken with that space telescope there. It's called the Planck Telescope. It operates at microwave wavelengths. And what you see in the picture there are very small fluctuations in temperature of what we call the microwave background. This is the afterglow of the Big Bang. And the statistics, it looks just like noise, but the actual statistics of that pattern there, what looks like noise, actually has a lot of information embedded in it. And it's actually one of the most reliable tools that we have for measuring things about the contents of the universe, how much dark matter, how much dark energy, things about the expansion history of the universe, the early distribution of fluctuations that eventually evolved into galaxies and clusters of galaxies. All of those things can be measured by computing the statistics of this image here. But there's an additional wrinkle to this, is that we're actually looking at that image not just through empty space, but we're looking at that image of the microwave background through a complex distribution of matter, of galaxies and dark matter, of large-scale structure in the universe. And that matter actually exerts a lensing effect on this image of the afterglow of the Big Bang. And by modeling that, we, or more specifically this Planck collaboration, the paper is, I don't know how many thousands of authors, maybe it's just hundreds of authors, and then there's like hundreds of papers. So it's a huge undertaking, but it's actually possible to back out the effects of gravitational lensing by the sort of the integrated mass of all matter in the universe between here and the beginning of time. So that's kind of mind-boggling. And you can actually pull that all apart and use it to learn even more about the universe in terms of how matter is clustered together, how that evolves over time, how much matter there is overall in the universe. So again, another on huge scale. So now we're looking down from the scale of individual planets all the way up to the scale of the entire universe. We see these applications of this gravitational lensing effect, which was just a throwaway calculation for Einstein. Now informing on all sorts of different areas of astrophysics. So I'll close just with one last thing that connects back to something that I've been working on lately, or that mostly I've been talking with people who are actually doing the work, which is a new sample of gravitational lenses that lets us probe not just the so this is a collection of gravitational lenses by their nature, which let us measure not just the mass of the lensing galaxies, but they offer a chance of actually measuring the what we call the substructure. So the way in which that mass, that dark matter, the stars, the way in which they're clumpy and clustered, and the levels of mass substructure within the lensing galaxies, within the foreground galaxies. And that's important because that detailed substructure, the clumpiness of matter in our Milky Way or in any other galaxy, is one of the most robust predictions or expectations of our current theory of galaxy formation and dark matter, but it's something that's very hard to test. But it's something that we can test with this gravitational lensing effect. And the sort of just to bring this full circle, I gave away my last wine glass. Does anyone have a? So just for illustrative purposes, actually, it's perhaps good that these are cheap wine glasses from Dollar Tree and not like really well-formed, smooth wine glasses, because you can see that based on the fact that there are sort of bumps and ridges and wiggles in the base of these glasses, that what you might think of as substructure in the base of the wine glass actually translates into complexity in the images that you see. So you don't see smooth images like the one that you get from that nice, expensive margarita glass there. You see things that are more kind of chunky and messy. But in applying this to measurements out in the universe, that actually being able to measure the degree of chunkiness, or how badly formed is the wine glass, that actually in itself becomes a really difficult but really compelling measurement and a test of our current theory of galaxy formation and of dark matter. So I will leave this up for people who want to continue to sort of fiddle around with looking at that image, and thank you for your time.